Okay, can you all hear me? Okay, good. Okay, so before we begin, I saw that Alyssa Gomez is asking a question. Is there a reason why we can't submit assignment 20 and 21? Shows that it counts as 0 points. Somebody asked me that question, and I think it was from your same course, and I'm sure I corrected it. Let me just do a quick check and make sure that I've done so. Hold on 1 minute. Assignments 20 and 21. Okay, from what I see, it is out of 100 in each case. And let me just check something else here. Assignment 20, I'm just going to see if it will allow for you to upload your stuff. Okay, so as far as 20 is concerned, it is fine. And as far as 21 is concerned, let me see here. That should be okay as well. So as far as I see from my end, you should be able to upload those assignments. Assignment 21 lets you submit, but I can't submit 20. I don't know why not, because according to this allows for file uploads, submission type, file uploads. Hold on, let me go back to 20. This is 21, I'm sorry. Let me go back to 20. 20. Yeah, as far as I see, you should be able to upload your, I don't see why not. The points have been set and the file upload box has been ticked from my end, so I don't know what the issue is. What I can do is I'm going to call Canvas, the company itself, and see if I'm doing something wrong. But as far as I see, on my end, you should be able to upload your assignments. So can we email it to? Oh, okay, yeah, you can email it to me. That's fine as well. But I'm really curious about why this thing is not allowing you to upload specifically for assignment 20. But I'll look into it. But yes, you can email it to me as an attachment. Okay, somebody's asking, are all these assignments 16 to 20 now audio Friday? If you can, do as many as you can and submit it by then. But if not, no problem. I'll accept the late ones as well. All right. But try to do as many as you can. All right. So that's an answer to the question that Alyssa Fagalo, please forgive me if I'm mispronouncing your name. But yes, you can submit it even after Friday. All right. Okay, so with those questions out of the way, let me commence with or continue our discussion of chapter 11. Excuse me, hold on 1 minute. Let me check something here. Oh, let me turn on my video. Okay, so the last time we were here, we were talking about the rules for assigning electrons in the different orbitals. So what we're going to look at in this section is those rules at work for the first 18 atoms or 18 elements in the periodic table. Okay, so what we'll be concerned with is basically how the electrons are arranged. We won't be concerned with how the protons and neutrons are arranged in the nucleus. All we need to know at this stage is that whatever the number of protons that you have in a nucleus, that will be equal to the number of electrons outside the nucleus, all right? So for example, in the case of the fluorine atom, there are 9 protons in the nucleus. There's a total of 9 electrons around the nucleus in the fluorine atom. Same is true for sodium, 11 protons, 11 neutrons. I'm sorry, 11 protons, 11 electrons. And in the case of magnesium, 12 protons, 12 electrons, right? As you can see here, we have a certain number of neutrons, but remember, the number of neutrons is not fixed for a particular element because you have isotopes. So you can have the same element or atoms of the same element, but they have different number of neutrons, all right? Okay. One more thing I want to talk about before we get into the electronic arrangement of the atoms. There are a couple of ways that we can represent the distribution of the electrons. We call it the electron configuration. And we use this sort of symbolism here, all right? So just to explain what this means in this particular case, the 2 here would represent the principal energy level or the shell number, all right? So that's what the 2 here represents. The P here represents the type of sublevel or orbital, and the 6 here represents the total number of electrons in that particular sublevel, all right? So basically what this is telling you is that there are 6 electrons in the P sublevel, which belongs to the shell number 2, all right? So you're gonna see this kind of representation to indicate the type of distribution of electrons that would be in a particular atom. Now, what we're going to do now is look at how the rules that we discussed earlier, how they actually come into play when it comes to distributing the electrons in an atom. And we're talking about the most stable or the ground state atom in these cases, all right? So we'll be looking at how the orbitals will be filled. So we're going to use another representation where the boxes represents orbitals, all right? So this is a different kind of diagram or representation of how the electrons are distributed. The electrons in this sort of representation are indicated or represented by arrows, and the arrows are pointing either up or down, which indicate the spin. If you remember, we said that electrons occupying the same orbital must be spinning in 2 opposite directions, all right? So that's why we have the arrows shown here, and you're going to see how we place them in the correct orbitals, spinning in the direction that they should be spinning. So the first thing we're going to talk about is how the electrons are filling the 1s level. And we're going to start with the simplest element, which is hydrogen. And we all know that hydrogen has an atomic number of 1, which means that the hydrogen atom has only 1 electron. And that 1 electron will go simply to the lowest energy orbital, which would be the s orbital of the first shell, all right? So basically that's where the electron is going to end up. And that is what this represents here. So this box here represents the 1s orbital, and the electron will be occupying that orbital by itself. So that's basically the electron configuration of hydrogen. The other way of representing it is basically this symbolism right here, 1s1. So remember, the 1 represents the shell that the electron is located in. S represents the subshell, and the 1 here, which is written as a superscript, represents the number of electrons within that subshell, all right? So this is the shorthand way of representing the electronic configuration of hydrogen. The next orbital is, well, the next element, I should say, is helium. So to get from hydrogen to helium, which has an atomic number of 2, all we have to do is add an electron to the electron configuration of hydrogen. So this begs the question, where will that electron be added? Well, we know that the orbital, the 1s orbital, has a maximum capacity of 2 electrons, so it can hold up to 2 electrons. So the first electron, which was there in the case of hydrogen, will be here, and then the next electron will simply go into the same orbital, but will be spinning in the opposite directions, as you can see here. So in the case of helium, both electrons will occupy the 1s orbital, but they'll be spinning in opposite direction. And in terms of the shorthand way of writing down the electron configuration, it will simply be 1s2. So 1s2 would be the electronic configuration of helium, all right? Okay, so that's simple enough. So let's move on to a higher atom, where now we'll be looking at the electrons filling the 2s sublevel. So the next element in terms of the number of electrons would be lithium. So in the case of lithium, to get from helium to lithium, all we have to do is add an electron to the electronic structure of helium, I'm sorry. So in the case of lithium, you're going to have the first 2 electrons in the 1s orbital, and that orbital will be completely full, because remember, that's a maximum capacity of any orbital. So therefore, the 3rd electron will simply go into the next higher energy orbital, which would be the 2s orbital. So therefore, this is how the electrons will be distributed in the case of lithium. And in terms of the actual electron configuration of lithium, it will simply be 1s2, 2s1, right? So basically, this is showing you that you have 2 electrons in the s subshell of the first shell and 1 electron in the s subshell of the second shell, all right? So this would be the electronic configuration of lithium. The next element in this series will be beryllium. To go from lithium to beryllium, we add 1 electron to this system here. In fact, more specifically, that 1 electron will be added to the 2s orbital here, like so. Again, because there are 2 electrons in this orbital, they'll be spinning in opposite directions, and therefore the electron configuration for beryllium would be 1s2, 2s2. All right, so that's basically how we have the 2s orbitals being filled up. All right, so at this stage, the 1s orbital and the 2s orbitals will be completely full. So now we get to the next element in the series where we'll start adding electrons to the 2p sublevel. So that element, the next element will be boron. So what we have so far are the electrons distributed, the first 4 electrons distributed between the 1s and the 2s orbital. Boron has a total of 5 electrons. So this begs the question, where will the 5th electron go? And the answer is very simple. The 5th electron will enter into the next higher energy sublevel, which would be the 2p sublevel. And more specifically, the next electron will enter into any one of these 3 sublevels. All right, so it doesn't matter which one you assign it. So we're just going to put it here in this p orbital right here. All right, so therefore, this would be the electronic configuration of boron in terms of this diagram, and in terms of the this designation here, this would be the electronic configuration represented here. And as you can see, basically, you can see the correlation between this and this, where you have 2 electrons in the 1s sublevel, 2 electrons in the 2s sublevel, and the 5th electron will be occupying the 2p sublevel, and more specifically, occupying one of the 2p orbitals, all right? Okay, the next element in this series is carbon, right? So in the case of carbon, to get from boron to carbon, all we have to do is add an electron to one of the other 2p orbitals. So therefore, we're going to add that electron there. And this would be the electronic configuration of carbon, all right? And then when it comes to the next element in this series, nitrogen, the next electron that is added will be added to the vacant 2p orbital, which would be here. And therefore, that would be the electronic configuration of nitrogen. So at this point, all of the 2p orbitals will be singly occupied each by an electron. And please note that the way the electrons are assigned, they're spinning in the same direction. That's another thing that you need to keep in mind. The electrons that are added to the set of 2p orbitals here, each occupying an orbital by itself, will be spinning in the same direction, all right? Okay, so that's as far as nitrogen is concerned. So the question now becomes, what about the next element, which is oxygen? Well, in the case of oxygen, you have to add 1 electron to the system that is already there for nitrogen. So the question is, where will that electron end up? And the answer is that that electron can be added to any one of these 2p orbitals here. However, when you add that electron to any one of these 2p orbitals, that electron must be spinning in an opposite direction to the electron that was there before. So therefore, we're going to put this electron right here. And as you can see, they're spinning in opposite directions because they're occupying the same 2p orbitals. So this would be the electronic configuration of the oxygen atom. And you can represent it this way, 1s2, 2s2, 2p4. All right. Then the next element in this series is fluorine. And in the case of fluorine, to get from oxygen to fluorine in terms of how the electrons are distributed, we add 1 electron to either this 2p orbital or this 2p orbital. It doesn't matter. So what we're going to do is add it here. And this would be the electronic configuration of the fluorine atom. Or you can represent it as 1s2, 2s2, 2p5. Same thing, all right? And then now the next element would be neon. And to get from fluorine to neon, all we have to do is add an electron to the remaining p orbital, which is singly occupied. So it's going to look like that. and therefore the electronic configuration for neon is going to be 1s2, 2s2, 2p6. All right, so that's basically how the 2p sublevel will be filled in terms of assigning the electrons to the correct orbitals for the elements from, what was it, boron to neon. All right. Okay. Any questions so far about how the electrons are assigned? Any questions? Any questions? Okay, so let's talk about the next sublevel in terms of energy, and that would be the 3s sublevel. So we're talking about here determining the electronic configuration of sodium. So to get from neon to sodium, we add one more electron, and that electron will now move into the 3s sublevel because all the previous sublevels are completely filled. So therefore, the added electron has no choice but to enter into the 3s sublevel. So what you're looking at here is how the electrons are distributed among the different orbitals in the case of sodium, and this would be the electronic configuration for sodium. All right. The next element would be magnesium. Now, to get from magnesium to sodium, we add one electron, and that added electron will be added to the 3s sublevel, which is half filled, right? Which means that the electron that is added will be spinning in the opposite direction, but occupying the same orbital as the first electron here in the 3s sublevel, all right? So this is how the electrons are distributed in the case of magnesium, and the resulting electronic configuration is going to be 1s2, 2s2, 2p6, 3s2, all right? So that's the electronic configuration of magnesium. All right, so basically we have looked at how the electrons are added to each orbital as you go from one element to the next. And what you're looking at here in this chart is basically a summary of what we just did, actually, starting with hydrogen and ending with neon, right? So these are the diagrams representing how the electrons are distributed. And over here to the extreme right would be the electron configuration, all right? So basically, based on what we have done so far, you can figure out not only the electron configurations from hydrogen to helium, but even beyond, as we're going to see shortly. Well, actually, we see it right here. So we did up to magnesium, which is this electron configuration. So therefore, the next element is aluminum, which means that you have to add an electron to the next higher sublevel, which would be the 3p sublevel, and that electron will be added here. And then in the case of silicon, the next electron will be added to another p orbital. And then when you get to phosphorus, the next electron is added to the other p orbital. And then from there, you start pairing electrons when you get to sulfur, chlorine, and argon. The next electron will be paired up with this electron right here, spinning in the opposite direction. Same thing happens here in the case of chlorine, and the same thing happens here in the case of argon. And you see the corresponding electron configurations for these different atoms, all right? So what we have done so far is look at how the electrons are distributed among the different orbitals from hydrogen, which is the first element, to argon, which is the 18th element. Okay, so what we're going to see here now, in fact, before we even do that, okay, let me not, I was thinking of doing something, but let me not do that right now. We'll do that later. Okay, so what we're going to look at now is the relationship between the electronic structures that we just discussed and the positions of the elements in the periodic table. And what you're going to see is that there's a correlation, right? You're going to see that the, how should I put this? The position of the element in the periodic table is directly related to the electronic configuration of the atom of the particular element, all right? But let's talk about some background history. And I think I mentioned this before about the origins of the periodic table. The person that is credited more often than not with the first periodic table is a Russian chemist by the name of Dmitry Mendeleev. And he came up with the first version of the periodic table in 1869. Another person independently published the periodic table based on the known elements at the time. But Mendeleev tends to be given the greater credit. I don't know why really, but that's basically how most textbooks record the discovery or the first person to establish a periodic table. Now, in those days, the structure of the atom was not known, right? So, back then, they had no concept of protons and electrons and so on. So therefore, there was no such thing as the atomic number that was known then. So what was used in order to place the elements in terms of their order was the atomic masses, right? So the old periodic table that Dmitry Mendeleev came up with had the elements arranged in order of their increasing atomic masses. And he found out that after so many elements, they tend to repeat in terms of their properties, right? Now, of course, we now know, as I said before, that the positions of the elements in the periodic table is related to the structure of the atom, but Mendeleev did not know that at that time. He had no idea about the structure of the atom, so all he could do was report what he observed in terms of the arrangement of the periodic table that he came up with based on the atomic masses of the elements that were known at the time, all right? Okay, so of course, over the centuries, couple of centuries, other elements were discovered, and as a result, there were modifications, major modifications to the first version of the periodic table until we get the current version of the periodic table, which is what you're looking at here, all right? And this is basically the periodic table that we're going to look at to see the correlation between the positions of the elements in the periodic table and their electronic configuration. But before we get to that, there are a couple of things that we need to talk about with respect to the periodic table, the modern periodic table. The rows in the periodic table, we call them periods, right? And they're numbered. So you have period 1, 2, 3, all the way down to period 7, all right? So the rows are called periods. The groups, or I should say the columns, are called groups. Oh, before we get to that. So there is a correlation with respect to the period number and the atomic structure or the electronic structure of the atoms, right? And that is that the period number represents the highest occupied energy level of the atom, all right? So for example, all the elements here in period 4, if you look at their electronic structure, you'll see that shell or energy level is the highest one that is occupied by electrons, all right? So that's one correlation that you'll notice between the electronic structure and the positions of the elements, in this case, within a particular period, all right? Now, the columns, I was about to say, are what we call the groups or families, all right? And what we'll see as far as these columns are concerned is that in this system, they're numbered with a number and a letter. Now, let me just say this. This periodic table, or this system, I should say, where you have, for example, this column here is called group 1A, and this is group 2A, and then you have 3B, 4B, etc. This is an older system, which is still in use today among chemists. And I don't know the reason why this happened, to be perfectly honest, but I remember by the time I got to college, or by the time I graduated from college, another system was adopted where the group numbers are numbered directly from 1 through to 13 right across. I'm sorry, from 1 through to 18 right across. So the newer version of the periodic table would have this being called group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way to 18 here in the case of the elements to the extreme right of the periodic table, all right? However, the older system is still useful because what you'll find is that in the older system, these elements here on this side and these elements here on this side, they are called representative elements, right? And they're designated by a number in each case for each group and a letter. So this is called group 1A, this is called group 2A, and then over here you have 3A all the way to 8A here, right? Now, the thing about the representative elements, and more specifically about their numbers, is that the group numbers represents the number of electrons that is present in the highest energy shell. Let me just jump this, go to this slide here. So as stated here, for the A family elements, the valence electron configuration is the same in group each column. Now, I have not defined what we mean by valence electrons, so let me do so now. Write it here. So the valence electrons the electrons in the highest energy shell of the atom. All right. So that's what the valence electrons are, right? So the group numbers for the representative elements represent the number of electrons in the highest energy shell, and these are called the valence electrons. And the shell is called the valence shell, right? So for example, the elements in group 1A, you'll notice that there's one electron present in the valence shell. In the case of group 2A, it's 2. For 3A, it's 3, and so on, all the way to 8A, all right? Now, in the case of 8A, there's one exception, and that is helium. All the other atoms in the case of group 8 has 8 electrons in its outer shell, but helium is kind of unique in that it has only 2 electrons in its outer shell. Now, you might be wondering, why is helium placed in group 8A and not in group 2A? The answer to that, we're going to see later on, but the short answer is that all the elements in group 2A, what they also have in common is that they have a full outer shell of electrons, all right? So therefore, in the case of helium, the outer shell can only have a maximum of 2 electrons, so therefore it's considered to be full. And these elements that have a full outer shell of electrons, they tend to behave very similar in that they're very unreactive, all right? So that's the reason why helium is placed here, all right, in group 8A, even though it has only 2 electrons in its outer shell. Okay, let me backtrack a bit and talk about another group of elements which are known as the transition elements. And in this system of numbering the groups, they're called the B group elements. So those are the elements down here, right? So these are called the transition elements. Now, the type of predictions that we made about the A group elements, we cannot do the same thing for the B group elements. And there's a long story behind that, which I won't get into. But for example, we cannot tell what type of ions will be formed and so on, whereas we can make predictions in the case of the elements in the A group. So that's all I'm going to say about that for now. Okay, so we talked about valence electrons. Oh, and another thing about valence electrons, which I forgot to mention, the valence electrons basically determine the chemical properties of the elements. So what you'll find is that elements belonging to the same group, for example, 6A or 7A, they tend to behave chemically the same way, all right? They tend to react in a similar fashion. They tend to react with the same type of other substances and so on and so forth, all right? Or as in the case of the group 8 elements, they tend to be very unreactive. And that's why these elements, they are called the noble gases or inert gases. All right, so I talked about helium. So this is talking about the exception of helium. So let me skip that and talk about what we call the abbreviated electron configuration. So as you can imagine, as you get to larger atoms, the electron configuration would become longer based on what we have looked at before. And what we have here is a situation where we can actually abbreviate it. Now, the way we go about doing that is stated right here. It says the electron configuration of any of the noble gas elements can be represented by the symbol of the preceding, hold on, wait a minute. Okay, this is not worded right. This should read, the electron configuration of any of the elements can be represented by the symbol of the preceding noble element enclosed in square brackets, all right? So please make a note of that. You can basically take out of any of the elements, right? So noble gas should not be there, all right? So what this is talking about is how do we write down a more abbreviated version of the element in terms of the electron configuration. So as an example, we're going to use boron, all right? Now the full electron configuration of boron based on the rules that we followed is this right here. So in order for us to write down the abbreviated version, what you have to do first is identify the group 8 element that comes before boron in the periodic table. So if you look at the periodic table, you see that the group 8 element that precedes boron will be helium. And the electronic configuration of helium is 1s2, which is represented by this blue part right here. So therefore, to write down the abbreviated version, what we do is replace the 1s2 with the electronic configuration, well, actually with the symbol of helium in square brackets, as stated here, all right? So the 1s2 here will be replaced by the symbol for helium in square brackets, and it's going to look like this, right? So the 1s2 here is replaced by this right here. The 1s2 represents the electron configuration of helium. So that's why we have helium here in square brackets. And then we simply write down the remaining distribution of electrons, which is what we have here. So this is the full electron configuration, or the unabbreviated version, and this is the abbreviated version. Now, in this case, there might not be too much of a difference you can observe in terms of the length of the number of characters that are needed. But if you get to heavier atoms, or atoms with more electrons like sodium, you're going to see a difference between the full and the abbreviated version of the electron configuration, I'm sorry. So let's look at the case of sodium. In the case of sodium, the full electron configuration is this: 1s2, 2s2, 2p6, and 3s1, right? So again, what we do is that we go to the periodic table and we look up the group 8 element that precedes sodium, and that element would be neon. So if you look at the electronic configuration of neon, neon is represented by this part right here: 1s2, 2s2, 2p6. So therefore, to get to the abbreviated version, what we do is replace this chain here of characters with the symbol of neon in square parentheses, and this is what you end up with, right? So this is the abbreviated version, and this is the unabbreviated version, all right, or the full electron configuration. And clearly you can see that the abbreviated version here is shorter in terms of the number of characters needed compared to the full version here, which has more characters, all right? So this shows you the utility of using this method of determining the electron configuration, or representing, I should say, the electron configuration of larger atoms. I think I have another example down here in the case of chlorine. Let me move this up here. In the case of chlorine, the full electron configuration for chlorine is shown here. Again, we look for the element in group 8, which precedes chlorine, and that again would be neon. So this part here would be the electron configuration of neon. So what we do is replace this with the symbol for neon in square parentheses, just like we did here. And therefore, as a result, this would be the abbreviated electron configuration of neon, all right? So that's basically how we go from the full electron configuration of a particular atom to the abbreviated version, all right? So, any questions so far? Any questions about electron configurations, abbreviated versus unabbreviated? Any questions? So if I were to give you this, if I were to give you oxygen, and I ask you to write down the full electron configuration of oxygen, what would it be? What's the first thing you would look for? Anybody? Well, okay, let's see what's in the chat. Okay, oh, all right, so somebody, 2 persons got the right answer. Okay, I was hoping to do it stepwise, but since you guys jumped the gun. So the full electronic configuration is 1s2, 2s2, 2p4, all right? And we know that because the atomic number of oxygen is 8, right? So therefore, we know that there are 8 electrons. And therefore, the first 2 would go in the S sublevel, 1s sublevel. The next 2 would go into the 2s sublevel. And then the remaining 4 would go into the 2p sublevel. Okay. So this is the full electron configuration. So what would be the abbreviated electronic configuration? Well, okay, let's see. Somebody in the chat says something. Okay, so yes, that would be correct. And that was who? Tarun Stepinski. Yes, Ms. Stepinski, you are correct. Basically, as I said before, to get to the abbreviated version, you look for the element that comes before oxygen in the periodic table, and that element would be helium. And this part here is the electronic configuration of helium. So therefore, the abbreviated electron configuration for oxygen would be helium in square parentheses, followed by 2s2, 2p4. All right, so that's basically how that is done. Okay, very good. So what shall we talk about next? Okay, the electronic configuration of argon is shown here, right? Now, here's where things kind of look kind of weird and takes a different turn when it comes to elements beyond argon, because what was found, and there's a long story behind that, which I won't get into. What was found was that, okay, let me just say this. Based on what we have covered so far, you'd expect that the next sublevel that would appear after 3p would be 3d. Well, it turns out that what was found was that actually the 4s orbital from the fourth shell is of a lower energy compared to the 3d orbital of the third shell, right? So therefore, after 3p, you're going to have 4s, and then you're going to have 3d, all right? So the next element, which is potassium, the electronic configuration would be this, where the next electron, the 19th electron, will be added to the 4s orbital and not the 3d orbital, because the 4s orbital is of a lower energy compared to the 3d sublevel, all right? So therefore, this would be the electronic configuration of potassium, all right? And this would be the abbreviated version, right? Because of course, this part here is the same as the electronic configuration of argon. So therefore, basically replace this with argon in square parentheses, and then we have 4s1. And then the next element would be where we add 1 electron to the same sublevel here, the 4s sublevel. That's calcium, by the way. So therefore, the full electronic configuration of calcium is shown here, and the abbreviated version would be what we have here, all right? So these are the electronic configurations of potassium and calcium, respectively. So, you know, this begs a question, well, what about the higher orbitals? What order do those orbitals have when it comes to writing down the electron configuration of pretty much any atom beyond potassium and calcium and so on? Well, this chart that you're looking at here is what is used to make predictions about the order of the orbitals in terms of their energy, right? So basically, let me explain how this chart works. So when I was a student, what I would do in order to remember this is that I would write 1s, 2s, 3s, all the way down to 7s on one side of the paper. And then I would start with the second shell here with 2p in the next line, 2p, 3p, 4p, all the way down to 7p. And then the next line here, I would start with 3d, 4d, 5d, 6d. And then the next line here, I would start with 4f, 5f. And then I'll draw the arrows as you see here. And in order to establish the order of the orbitals in terms of their energy, I would start with this arrow right here at the top and follow the arrow from tail to head. So the first orbital would be 1s, and then the next in line would be 2s for the next arrow, and then the next in line would be 2p, 3s. So you basically follow all the arrows from the tail to the head, going down to get the order of the orbitals in terms of their energy. So basically, based on this diagram right here, this would be the order of the orbitals. Let me write it right here. It's going to be 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d. And remember I said that the 4s comes before the 3d? Well, that's how we got it from this diagram right here. And then after 3d, you're going to have 4p. And then after 4p, you're going to have 5s, and so on and so forth. You basically go down by following each arrow from tail to head, all right? So if you have this diagram here at hand, then you pretty much can write down the electronic configuration of almost any atom that is present in the periodic table. So for example, if you were asked to write down the electronic configuration of, let's say, titanium, let me see here, what's the atomic number? I think the atomic number, hold on. The atomic number of titanium, I think, is 24, because calcium is 20. No, actually 22. Calcium is 20, then scandium is 21. So titanium is 22. Okay. So in the case of titanium, the electronic configuration would be, okay, let me just use this since I have this here. The electronic configuration of titanium would be 1s2, 2s2, 2p6, 3s2, I'm sorry, 2, 3p6, 4s2. So that's 20 electrons so far, and therefore the next two would go here, right? And you would need to write this down, all right? So basically, this would represent the electronic configuration of titanium, all right? Okay, so how am I gonna do this? Okay, I know what I'm gonna do. Let me get out of this here. Okay, and what I'm gonna do is kind of like a split screen kind of thing. Okay, hold on 1 minute. Okay, I want to keep this diagram up so that you can refer to it. So, let me see here. I know what, let me check over here. So I'm just going to choose an arbitrary element. So the element I'm choosing is cadmium. No, not cadmium, I'm sorry. Yes, cadmium. All right. So cadmium has an atomic number of cadmium has an atomic number of 48. All right. So therefore it has 48 electrons. So using this diagram, what do you think the electronic configuration of cadmium is? Well, Okay, so any ideas? How many electrons will go into the 1s orbital? Okay, so 2. And then the next orbital would be what? Two S2. And then the next orbital will be what? 2p6. Very good. And then the next orbital will be what? 3s2. And then the next orbital will be what? 3p6. And then the next orbital will be what? 4s2. And then the next orbital would be? Nope. It's not 4p6. Look at the order, right? After, where is it? After 4s2, after 4s, you have to start at this arrow here. So the next orbital will be what? Exactly, 3d10. So let me put 3d10 here. And then let me bring this down here so you can see that. After 3d10, then what? Okay, hold on. After 3d10, then there is 4p6. And then after 4p6, then what? I don't have enough space here to see all of this. Okay, so after 4p6, there's 5s2, that's correct. And then what? After 5s2, then what? Four D10, exactly. Okay. 4D10. And that would be the full electronic configuration. If you count up all these electrons here, you're going to get a grand total of 48, which is the atomic number of cadmium. Okay, very good. So the next question is, what would be the abbreviated version? What would be the abbreviated electronic configuration of cadmium? So the answer to that lies in finding out which group 8 element comes before cadmium in the periodic table. So which group 8 element comes before cadmium in the periodic table? Come on, you should be able to find that. You should have a periodic table nearby. Well, okay, so somebody jumped the gun. Okay, so based on your answer, you're saying that krypton would be the group 8 element that precedes cadmium, and you're right. And the atomic number of krypton is 36, which would mean that krypton will have this electronic configuration right here. So that would represent the electronic configuration of krypton. So therefore, the abbreviated version would be krypton in square parentheses, and then that followed by 4s2. I'm sorry, 5s2, 4d10. All right. So that would be the abbreviated electronic configuration of cadmium. All right. So basically, if you understood what we just did, you should be able to write down the full electronic configuration of any particular atom in the periodic table. And based on that, you should be able to determine the abbreviated version. All right. And of course, in order for you to get the full electronic configuration, you're going to need to use this chart right here. This is the chart that you're going to use to determine the electronic configuration of a particular element. Okay, so are there any questions concerning how do we determine the full electronic configuration and the abbreviated version? Any questions? Okay, so let me go back to the PowerPoint here. No, that's not it. Let me go back to full screen. All right, so that's as far as that is concerned. Now, based on what we have just learned, you're going to see certain patterns emerging in terms of the placement of the elements in different regions of the periodic table. And that's what this diagram is all about here. So this is showing you basically, as you go from one element to the next across a particular period, which sublevel is being filled specifically. So if you look at this part here, right, where you're going from an element in group 1A to an element in group 2A, basically what is happening is that you're adding an electron to an s orbital, all right? So this region here, whoops, did I skip something? Well, hold on 1 minute, let me, okay. So this region here, right, we call this the S block, right, which is colored pink right here, right? We call this the S block here. Now, on this side here, as you go from one element to the next across a period, what you'll find is that you're adding an electron to a p orbital. So this region here, which is colored purple, we call it the p block of the periodic table. And then this section here, where as you go from one element to the next, you're adding an electron to a d orbital. This region here, which is colored green, is called the d block. And then finally, in this case here, where we have what are known as the inner transition elements, you're adding an electron as you go from one element to the next across a period. You're adding an electron to an f orbital. So we call that the f block. All right. So those are different regions in the periodic table, which has their own special designation, purely based on how electrons or to which orbitals or sublevels electrons are being added to as you go from one element to the next across a particular period. Now, so here, as we said before, an electron is being added to a d orbital. So that's why it says your d orbital filling for that region. And one special thing you need to note in this region is that the number of a d orbital that is being filled here would be one less than its period number. So for example, here in period 4, it is a 3d orbital that is being filled going across here. Here in period 5, it is a 4d orbital that is being filled here. And you see a corresponding arrangement for period 6 and 7. Now, in the case of inner transition elements, what you'll find is that as you go from, for a particular period where you're adding electrons to a particular f orbital, what you'll find is that the number here, the principal quantum number here for that particular f orbital will be 2 less than the period number. In actual fact, this part here, this inner transition element block right here, the f block, actually should be right here in this section right here. And as a result, this period here is actually period 6. So you'll notice that the quantum number here for the F orbital that is being, or the F sublevel that is being filled here is 4, which is 2 less than 6. And the 5 here is 2 less than 7. All right, so that's another arrangement that you need to be aware of. Okay, so I think I mentioned this before, and I'm going to mention it again. A period number corresponds to the highest energy level occupied by electrons in a period. So it doesn't matter what period you're talking about. So if you look at period 6, for example, and if you look at the outer shell electron arrangement, basically what you're going to see is that the 6th shell will be occupied by electrons, right? In this case, the 6th shell will be occupied by electrons in either, or I should say either and, or either or, no. Well, either the s orbitals or the p orbitals of the 6th shell, all right? And that is true for all the period, all the periods and all the elements that are located within a particular period. The group numbers for the representative elements, and I mentioned this before, would be equal to the total number of electrons in the outermost shell of the atoms. So for example, I could choose any arbitrary example. For example, in group 5A, you'll see that starting with nitrogen and ending with bismuth, you're going to see that there are 5 electrons in the outermost shell of these atoms, all right? So that is true in the case of nitrogen, that is true in the case of phosphorus, arsenic, antimony, and bismuth, all right? So that's basically another general statement, which is true, well, always true actually, for the representative elements, all right? So as stated here, they have the same outermost electronic configuration, excepting that the electrons will be in different energy levels. So you can see that if you compare, for example, nitrogen to phosphorus, the electrons here, in the case of nitrogen in the outer shell, would be 3 electrons in the 2p sublevel and 2 electrons in the 2s sublevel. But here, it is 3 electrons in the 3p sublevel and 2 electrons in the 3s sublevel, all right? Okay, and that's basically it for this chapter. So there's nothing else to say about this chapter. So, and that's basically it for today, unless there are any questions you want to ask. But that's basically all I have for you today. Let me remind you that the test, number 1, is still online. Make sure you complete it. Make sure you follow all the instructions I gave you about completing it. Make sure you do it by hand, blue or black ink. Make sure you scan it as a PDF document and upload it into the Canvas portal for that particular assignment. And remember, it's due today at midnight. So if you have not turned it in yet, you have until midnight to do so. All right. Okay, I think that's all I have for now. Are there any questions? Any general questions you have? Okay, if not, well, that's it for today. So enjoy the rest of your day and the rest of your week and the weekend, and I'll see you guys. Oh, before you leave, how could I forget? Let me let you know what assignments you need to be doing. So let me go to here, and let me go here, and let me go to assignments. And so this will be chapter 11. Oh, no, actually chapter, wait a minute. Yes, chapter 11, what am I saying? Chapter 11. Okay, so basically the assignments that you'll be doing for this chapter will be assignments 31. We'll publish that. And 32. All right. And yes, so those are the assignments that you need to do for that chapter. So I would say make sure you do those by next week as well, next week, Wednesday. All right. Okay, so if there are no questions, that's pretty much it for today. Oops.
So assignments 17 through 29 are due Friday.
Well, as I was saying before, if you cannot complete those by Friday, no problem. You can take your time. I'll collect them next week as well.
Okay.
Because I know it's quite a lot. Plus, you guys have the test to do. So, all right. Any other questions? Okay, so that's it for today. So I'll talk to you next Wednesday. All right. So have a good day.